All right, good morning. For those of you that are online, if you'll just type in the chat, I'll watch the chat for any questions if you have any that come up. All right, for you guys that are online, are you able to see my screen? Try this again. Hopefully now you can see the screen online. Great. All right, good morning. Apologies for being a little bit late today, one of those mornings. So, all right, last time we talked about the postponement of the assessments and quiz. So I've posted those. You can find them just even on the homepage. These are under also the modules. So I have posted, you have the assignment, tell me about yourself. A lot of you have already done that, but if not, just make sure you do it by Thursday. And then the assignment week 2 discussion is to post a question and you can answer it yourself or ask others for help. So that's supposed to be, you know, a discussion board amongst the whole group. So you get credit for just posting and responding. So just do that by Thursday. Then the RL assessment and the RC assessment. So this is where you're going to be able to locate those. I do suggest going through the learning material first. I have updated the learning material. So on the learning material, there we go. So it has all of the sections. I included some of the math that some of you may not have seen yet in your math classes, and hopefully that's enough. But if you have still questions on the math, feel free to open it up as a question in here. And I can go into more detail if that is helpful for you to be able to then apply it, which is what we're really looking for, is the application of how do you use this math to solve these problems. And so on the RC and the RL, I have also included a test your knowledge. So I suggest going through these. And then if you're struggling with these, there are all these examples down here now. So for the RC, there's all these examples. And then the RLC are all of these examples. So hopefully now there's enough material in here to be supportive of like, okay, I can go and work through these problems. So please do go work through these. I don't do a lot of homework. So instead you just need to work through it at kind of your own pace to say, do I really know it or not? So everybody does learn differently at different speeds. So if you don't need to do busy work, I'm like, don't do busy work. But if you don't stay on top of it, it will be difficult to do well on the exam. So do make sure you go through as many of these examples as you feel like, okay, I do understand the material now. Yes, Taylor.
Are these examples a good barometer? Like if we can handle these examples, Is it a good barometer for the types of questions we'll get on the exam for the midterm?
Correct, yes. Yeah, so, yeah. You're gonna see also the types of questions I ask in here are very indicative of what we'll have on the exam.
Okay.
So that first exam will have RC, RL, and RLC. So hopefully that's really straightforward. It'll be a problem on each of those. And then I usually try and put in like a 10-point kind of more understanding question, which we'll kind of get to closer to the exam. Yes.
So with the RC and RL,
Uh-huh.
is it entirely open note or is it like you have one sheet of?
Good question. So his question is about the assessments and probably quizzes and exams. So on the assessment, everything is open book, open note. There's no time limit on the assessment, so you can actually start it, go away, work on it, and then come back to it. So you can actually see, you can do it up to 5 times. So if you want additional practice, it will just take the highest score out of your 5 attempts. So if you are wanting new problems, that would be another way. Each time it will bring up a different problem for you. Or it's supposed to bring up a different problem for you. So there'll be unique problems each time, and there's like a database of, I think I did like, let's see, 10, 20, I think there's like 20 questions in there. So there's quite a few questions in there that you can keep trying to assess yourself and see how you're doing. For the quizzes, it's also open note, open books, and for the exam, but I do suggest that you have even, compiled a sheet front and back of your notes so that it's easier to find the information you want. So for the RLC, you're going to want that table for sure, so things like that. And then the ones I said, memorize these equations, I would just have them written down in case you get a little nervous, just so they're really handy. So not required to have that, but I would have it handy. So I don't want you to have to spend a ton of time creating the sheet, but I would suggest like, okay, a couple sheets that are easy for me to flip through these to find that information quickly, the equations and the steps. And I would write things out in your own words as far as the steps and procedures of how you solve the circuit. That makes sense? Yes.
And it's mostly the same day they're due, so it's.
Yep. So anytime that morning, you have, I think it's 100 minutes. So you have pretty much like a class time period to do it in. And it's 8 a.m. to like midnight. So just any time in between there. It's not designed to take 100 minutes. It's just one problem. And it's, most people should be able to get through it, in a half hour at most. And, if you're ready for it, you could even probably do it in 15 minutes. So hopefully it won't take you too long, but it is a good, and those are also another way, Taylor, you'd asked about the type of questions. Those are also another good way to say, okay, this is what I'm going to probably expect to see on the exam. So those quizzes are a good way to self-assess also, like, how am I doing and do I know this material? All right, any other questions? Yes.
So looking to the examples of the RC and RL, there's one example of dependent sources. And I was wondering like how many like problems we have with dependent sources.
So we haven't gone over the dependent sources, but there are a couple examples like on here for the dependent sources to give you extra practice on them.
Okay.
So you could see a dependent source on there, so do be prepared for that. And we'll go over some more of those problems as we get closer to the exam. Other questions? Okay, online, let's see. The assessment, okay, online asked about, is the assessment multiple choice? So how I've done the assessment is that you have a box. And so you just have to put in the number. It says, it will say either round to the nearest whole number, or it will say, do it in the form of X dot, to the 4th decimal place. So just write it out in that form to the closest value that you have. And then you're going to upload your partial work, and then you'll get credit. If you didn't get the right answer, you'll get credit for the partial work that you do. Is that clear, like how you'll be expected to do that? I was going to make a multiple choice, and they got to be 50 answers. And I was like, okay, we're going to do this differently so that it's a little easier to grade. So it is just work out your own problem and then put the answer in a box. And so part of that, I'll kind of go over an example today of where I give you like a number T equals some number and you're going to plug it in and then see what value you get. And so that will be what it will ask for. All right, is that answer your question, Sam? Okay, great. All right. Okay, so I did post new notes, so if you want to grab them from online. This again was from last time. Do make sure in your notes that you correct this equation. I apologize that I have those parentheses wrong. So it should be for the RL and the RC that the final is by itself, and then initial minus final is one quantity times e to the minus t over tau. So do make sure to correct both of those in the notes. All right, as far as capacitor inductor, I had also put on the other pages, there's a goal of them, which is for the goal for the capacitors to make sure you understand how it operates. So how do you use it in a circuit? And for us, we're going to look at, okay, if it's been sitting there for a long time, what happens to it? You model it as an open, correct? So that's the understanding you have to take away from that. The other understanding of that is that once it switches and there is a small change, it acts like a battery. So those are the two main concepts of a capacitor that you need to understand. The RL, the two concepts is what happens to it after it's been sitting there a long time, it becomes a wire. And then as it changes, it acts like a current source, correct? So those are the two things that you need to understand from the capacitor and the inductor to apply them. Then RC and RL, when you have those circuits with a switch, you have to understand how do the background of where did this equation come from? And that helps to understand like, okay, if I don't have that and I have a different kind of circuit, how do I analyze that? And then using this equation, you have to find the final state, the initial state, and the tau. So being able to understand how to get each of those components and then plug it into this equation. And then, as I said, for the quiz, you're going to have to put in a value for T and then get an answer. And that will be how you'll put for the quiz and the assessment. All right, then we move to RLC. So now we have, okay, it's a little bit more complicated circuit. RLC are all in there. There's two forms of RLC. They can be in parallel together or they can be in series. So when we look at one of these circuits, we have to identify, is this circuit a series connection of these components or a parallel connection of these components? Then from there, you have to find that alpha and omega naught. And so depending if it's series or parallel, you're going to get a different alpha. And then omega naught will be the same for both of them. From there, you're going to then determine, is it overdamped, critically damped, or underdamped? And using those equations once you identify what those are. So that was what we had started last time, was we went through this equation, or this circuit, sorry. And we were trying to find VC of T. And then note on these, when you're in series, you need to find the voltage across the capacitor. You then use that value to find any other voltage or current in the circuit. For parallel form, you're going to find the current IL, and from there, you're going to use that to find any other voltage or current in the circuit. So do also understand what component can I find from these. Okay, so parallel form, we're going to find current through the inductor. Series form, we're going to find the voltage across the capacitor. Yes.
So if you're using finding current, then you want to find a different that some different source out whatever is potential or final. Every value we got. Does that make sense what I'm saying?
Yeah, so a little bit different. You're going to use it like it's even though it's in an equation form, you're going to use it as if it's like a constant. So you would treat it. So say, for example, you wanted the voltage across the resistor, you know, after you've in the parallel form, and you know that IL. Then you're going to know that, sorry, you know, it depends on what the other part of the circuit does, but you can either use a current summation, just treat that IL as like a constant and a variable until you solve it in the form of IL. So whatever voltage across that resistor needs to just be in the form of IL, and then you would plug that into it. Does that make sense?
Yes.
If you wanted to find like the current going through the capacitor and you knew IL, it would be the same thing, but you would model it either as an open, and it depends on when you want to find it. So we'll go through an example like that, but that kind of, hopefully that makes a little sense, and then we'll go through some problems with it. Is there another question? Thought I saw a hand. Okay. All right, so we had identified that this was, what was this circuit? Do you guys remember? Series or parallel form? Correct, series. And it's identified as series because of when the switch in the final position is when you determine which form it is. So in this case, in the final position, that is open, and then you can see that they are all in series together. If it's closed and you look at it, it does look like they're in parallel form. So that's a little confusing. And so you do it at the final state. So series, then you found, so first identified, what do I have, series or parallel form? Second step was to find alpha and omega naught. So we found alpha and omega naught, saw that they were actually equal. So then this third step is to identify what type do I have, critically damped, underdamped, or overdamped. And in this case, with them equal, it's critically damped. So then I don't need to memorize those equations, but I have those handy and I can say, okay, now I need to find these values. I need a VC of 0, which is the initial value for the voltage across the capacitor, final value, VC of infinity. IC of 0 is the current, initial current going through that capacitor. And then I use that and just plug it into those variables. And then from there, I can write the equation. So that was the fourth step, is to find initial value, final value for IC and VC. And then fifth one is to plug them into this equation. And that was how you get your answer. Okay. All right, you guys are going to start off with the same steps for this circuit. So at time equals 0, that switch goes flips. So in the first section, you're going to have an RC circuit. And then once it flips, you're going to have an RLC circuit. And so again, you look at this at that final state. So will this be series or parallel circuit? So you're going to use the series equation. So identify that it's in series, RLC. And you want to find the IC going through the capacitor. So this is a little bit harder in that I had said you have to find the VC first and then use the VC value to find IC. So in this case, how are VC and IC related? So the capacitor, this was another equation I said to memorize, and characteristic, oh, I forgot. That's the other thing you need to know about capacitor and inductor. So capacitor, you need to know the equation for it relating V and I. So what's that relationship for the capacitor? Correct. So this was the equation you have to memorize. And then for the voltage, you have VL is equal to L di dt. So memorize those equations, and then you're going to use that in this case. Once you get VC, you are going to take the derivative of it, multiply it by C, and that's how you're going to get that IC value. Okay. All right, go ahead and break up into small groups and work on getting this IC of T greater than 0. Introduce yourselves if you don't know your neighbors so that you guys can work together. All right, I'm going to put you guys into breakout room just so that you guys can chat without it going loud onto the sound on in the group. So if you guys want to take a screenshot of this so that you can then annotate it in the breakout room. Or if you want, one who wants to share your screens to annotate it, that seems to be easier to work together.
Hey, teacher, you're muted. Hey, teacher, you're muted. Professor Rasmussen, you're muted still. You're muted still.
Muted. Okay, hopefully you guys can hear me now. Thank you. I've never heard that. All right, so first step was identify series, second step alpha and omega naught, third step to identify critically damped and then use the equations. So now we're going through and finding that initial value for the capacitor, final value for capacitor, and initial value for current. So initial circuit is right before the switch happens. So determine which position is the switch in. And then I've been sitting there for a long time. So what happens to the inductor? Inductor becomes a wire, capacitor becomes open circuit. So then this becomes my VC. And so VC of 0 minus is going to be 40 volts. And then my initial value, and then there's no current here. And so when I redraw that, I redraw the current source at right as the switch happens. I replace that with a voltage source and the current source. This is going to be 0. This is going to be 40 volts. And so I can see that IC of 0 is also going to be just 0 because the current source is 0. So that gives me those two values. And then I need a final value. Again, sitting there for a long time. So inductor is wire, capacitor is open again, and the switch now is in this position. And so VC in this case is 0. So I identify all those and then I just can go back and plug them in here. So V1 was 40 and then minus 0 for the infinity. And then V2 is IC over 1 over IC, and IC 0 was 0. So this is 0 plus alpha. And then initial was 40 minus 0. So that gives me 400. So I plug that into VC of T, which is going to be this equation. So I have B1 plus B2 times T e to the minus alpha T, which is 10 plus 0. And then I differentiate that. And that ends up canceling out several terms. And I end up with a minus 10 400T e to the minus 10T. And then I multiply that by the minus or the 10 milli from the capacitor for C, and that gives me, I miswrote this. There's the T in there. Write that. So minus 40T e to the minus 10T. And then it's multiplied by U of T. And I've had several questions about what is U of T. So U of T so the unit step function and the exponential function are ones that you really need to understand well. So I've put in here some video lectures to help you understand them better. So please go through those to understand them better. Very quickly, what they are is the unit step function is any time I have a switch, it is going to look like a piecewise graph. So before the switch, I'm going to have some voltage, and then after the switch, I'm going to have a change of another voltage. So it's called a unit step function. Get to it. 354. There we go. Okay, so it looks like this where before you have 0, and then after the switch, it's going to turn on. So this is called a unit step function. And so it's defined as U of T is 0 before T equals 0, and then after it, it's a 1. And so because we have just a voltage source in there, that is what is acting as that unit step function. And so anytime you have just a DC voltage source, it turns into that unit step function because we have a switch in the circuit. So your answer is technically correct by putting that U of T in there. So it's 40T e to the minus 10T, and then it's only valid once T is greater than 0. So you could write this a couple different ways. The U of T just defines it as anything after time 0. It would also be correct to just say IC of T is 40T e to the minus 10T only for time greater than or equal to 0. So those are the same answers. You just need to understand that it's only valid after T is greater than 0. Sorry, it's not equal. It's just greater than 0. So either one of those answers, you can write it either way. But you are going to see, especially in the book, it will have that U of T. So I wanted to describe what that means. So all it means is that it's only valid for after time is 0. All right, questions about these steps? This is written out a much nicer form than mine. So if you want to look at that for a minute. Questions? Is it making a scary circuit look more realistic to solve? Okay. That's the goal. It's just like, this looks scary, but it actually isn't. There's methodical steps on getting the answers. And it's just more understanding what are the steps and where am I missing those steps. Okay. All right, any other questions? All right, we're going to move to another problem. So same steps again, is that we have this circuit and we want to create, when we want the equation to describe it, and then we want to look at like, what does that graph actually look at like this time? So first step is to do what? Before alpha. Correct. So determine if it's in series and parallel. And so how do we determine if it's in series or parallel? Where do we put the switch to find that? Final position. So in this case, it will be in an open position. So when it's open, it will look like this. So what does that look like? Series or parallel form? Okay, good. So series form will be what we'll have. So the first step is to identify, is it series or parallel? In this case, it's a series RLC. All right, then what? Correct. So I heard somebody say alpha and omega naught. So determine alpha and omega naught. So alpha is going to be an RTH over 2L. And omega naught is 1 over square root of LC, or square root of 1 over LC. Same thing. So RTH in this case.
Those are things that Rich remember from the fact that it's an RLC circuit, right?
Yep, this page. So this page is going to be what you want to have very handy. And then here you see that, okay, there's the equation for series RLC and then omega naught. So just have that sheet handy. I just haven't memorized, so I wrote it. Okay, so now we have to find RTH for this one. So we have independent sources here. Again, we keep it at the final position. So these are again at the final position. So for the final position, this again will be open. This will be an open because it's a current source. And then this will be open and we are finding, sorry, this will be a wire. And we're finding the equivalent resistance for series, remember, is across the capacitor. For the parallel form, it's going to be the inductor that you look at the equivalent RTH because you're finding that current IL is the goal there. So that's the other thing you have to understand in these is what component is my RTH equivalent from. So in this case, A and B is across the capacitor. So for series, alpha RTH from the capacitor. Okay. And then for a parallel form, again, it will be through the RTH will be from the inductor side. So RTH in this case is going to be what? Correct. These two, hopefully you see, are in series. So as I go through, they end up just in a series form. So 0.62. Over 2, and L is given as 0.05. And then omega naught is 1 over the square root of 0.05, and C, I erase C. C go. Have it there. Sorry. C is 1 over 1.8. I think this was 0.6.2. Let's see. Yeah, 6.2 and 6 for omega naught. So what do I have here? Okay, so alpha is greater than omega naught, and so overdamped. So this is the third step, is identifying which ones do I have. So now I go back to my sheet and I grab those equations. So overdamped. And this one, I see that I have S1 and S2 also in there. So I'm going to grab the equations for S1 and S2. So from that sheet, S1 and S2. I'm just going to write S2. S2 is the same, but a minus the square root of alpha squared minus omega naught squared. So S1 and S2 I can find right away. So alpha is a minus 6.2 plus the square root of 6.2 squared minus 6 squared. And S2 is minus 6.2 minus a square root of 6.2 squared minus 6 squared. That ends up being a minus 6 or yeah. Minus 4.64 for S1 and a minus 7.76 for S2. So I have S1, S2. So S1 and S2 in all of these. But I need VC of 0, VC of infinity, and IC of 0. So initial one, although, was there a question? Did it get answered? I heard somebody. Yeah. Okay. Any other questions? Yes. It was given. I had erased it on this one, sorry. L is given as 0.05 and C was the value of 1.1 over 1.8. I had erased it though, sorry about that. Yeah, in the original circuit, it was in there. Let me grab that and I'll repaste it on there. So this was the original circuit. All right, so initial value. The switch at 0 minus is in this position. L becomes that wire and C becomes an open. So you end up with this circuit. C is open, L is a wire, and then it is, the switch is in this position here. So VC of 0 minus is going to be what? How do we find it? Note that it is, there's no current going through the 0.52, right? It's a dangling wire out there. So that whole node, there's zero current here, which means there's also zero voltage across that one. So that node is all of the same up there. And then on the bottom, this is all the same. Okay. I call that VX. So I have this branch, which is, uh-huh,
Your ECE is the minus.
it's just VX, right? Because there's no voltage drop there. So that is VX. So VX is 4 milli divided by 1 over 0.1 plus 1 over 0.1. Which is 0.2 milli. Other thing I could notice is that 4 milliamps comes in and then 0.1 and 0.1 are equal. So it equally split. So I get 2 milliamps in each one, and then 2 milli times 0.1 would be 0.2 milli. But a lot of times you're not going to see that right away. So this is how you would go about it mathematically. So find VX. This is VC of 0 minus, oops, VC of 0 minus. IL of 0 minus is going to be what? From our equations, what will it be? It's the,
2 milliamp.
it's going to be 2 milliamps. What's the equation for it though? That's really dark.
4 milliamps times 0.1.
Correct. So that would be a current divider equation. So you can find it by a current divider equation. If I already know VX, it would be VX over 0.1. So 3 different ways to get it. If you visually see it, you can say I visually see it, but it's 2 milliamps. It's got to split equally. If not, the current in the branch through the 0.1 is IL of 0 minus, because no current goes into this branch. So this has all got to be 0 minus. Any of those methods, you can get that. Yes.
So why are we not looking at the 52 ohm resistor? It's like, you said that you had that 0.1 there.
It has 0 volts across it. It doesn't do anything. So the node is the same on the left of it as it is on the right. So you're basically like ignoring it because it is no voltage across it. It's a dangling wire, basically just kind of sitting out there dangling. Visually, I know it's kind of hard to visualize that, but that's what is happening there. All right, so I have now IL of 0 minus. So the initial is right as the switch happens. So in this case, I'm going to replace the inductor with what? Right as the switch has been changed. So it's 0 plus, meaning right when the switch changes. What happens to the inductor? Correct. I replace that with the current source. And its value is going to be this 2 milli. The switch is open, so I'm going to leave that right above that 0.1. And then what happens with the capacitor? It becomes a voltage source, correct? Same polarity as it had, and it is the value of 0.2 millivolts. This is in volts. So now I need to find IC of 0 from this circuit. So what will IC of 0 be?
Oh, no, sorry.
Okay, do you see it? It will be 2 milliamps because that's all the same branch, right? So all of this, oh, it doesn't go through. They're all in series. The 0.1 is just a dangling wire in there. So if I set that by a current source, that 2 milli is going to go through the whole branch. So my IC of 0 will be 2 milli. So this is the other. I have, this is VC of 0. This is IC of 0. And now I need just the one more. Yes.
Why doesn't the voltage source generate a current from like without polarity and like these events, like why does it do that? Or why do you see this the only thing coming into the voltage source?
So good question. So his question is, how do you know which direction that current through the inductor is going? So I don't. I arbitrarily choose it. And then if I had chosen it going the other direction, you would find it would be a negative. So I could still draw the current source going the other way and have a negative 2 milliamps.
But my question is more like about the voltage source. Is that not generated current? Or is it like the combination of the two would be the current?
So I kind of know because of experience that if my current source is forcing it in coming up, it's going to come in and split naturally where it's going to go down. So that's where I knew that the IL was going to go in that direction. But sometimes you don't know. And so you can just arbitrarily label it for that current direction. And then you would solve that part of it, find the IL, but find it would be a negative. So then you would just draw the current source in the direction that you labeled it and give it a negative value. For the voltage across the capacitor, I know that that current's coming down. And so again, it's going to be a plus, and the minus goes with the arrow side of the current source or the current direction. So that's where I know that it's a plus and minus on the capacitor. It was given already in the problem as that's the plus and the minus side of that capacitor. If it wasn't given, again, I could arbitrarily say, well, I don't know. So I'm going to choose a direction, solve for it, and then whatever value I get from that, I would use. All right, we are out of time for today, so I will finish up this problem on Wednesday, or wait, for Wednesday today. So no class on Monday. You will still have on Tuesday an RLC circuit assessment, and then you'll have a quiz on Wednesday to do. And it will be an RLC circuit. Yeah, quiz on Thursday. There will be an RC or RL quiz. Hi.
I just wanted to know if I'm good to drop out of the 24 months on this page so that
Just 1 sec. All right, have a good day, guys.